Okay, this is Project Test 5. This is video number 4 and covers problems 31 to 40. A test of hypothesis, mu equals 0 versus mu is greater than 0, is conducted using a sample of size 7. The test statistic was t equals 1.935. So we ended up using a t statistic of 1.935. This is our t value. And remember, t is centered on 0. And we have a sample size of 7, so our degrees of freedom is 6. And we have a greater than, so we're shading up and to the right. Very important to make note is whether it's a one tail or two tail. This is a one tail. So all I need to do is go stats, second bars, and I'm looking for the TCDF. My lower bound is 1.935. My upper bound is going to go to positive infinity. And my degrees of freedom in this case are 6. So I end up with 0.0505 or 0.0506. So 31 is D, is my best answer. Okay. All right. Number 32. And by the way, this did not copy very well. This is group A over here. This is group B over here. And this is group C over there. So as part of a community service program, students in 3 middle schools, grades 6, 7, and 8, each chose to participate in one of 3 school-sponsored volunteer activities. The graph below shows the distribution for each of these 3 activities. Now notice, we know the percentages, but we have no idea as to how many 8th graders, 7th graders, or 6th graders there are. There might be 1,000 8th graders and 5 7th graders, or we just don't know, all right? Of all the students who chose activity B, the greatest number of students were in grade 6. We have no way of knowing. The greatest proportion, 6th grade had the greatest proportion, but we don't know how many, so we can't say that about the greatest number. They had the greatest proportion, but not necessarily the greatest number. Grade 7 and 8 had the same number. Once again, yes, we can look and go, you know what, they had the same proportion, but we don't know how many 8th graders and how many 7th graders there are, so we can't say that about it. The grade with the greatest percentage of students, oh, here we go, greatest percentage of proportion who chose activity C was grade 8. It's like, okay, there's activity C, and it looks like that's false. Grade 7 had the most. For students in grade 7, the number who chose activity C was greater than those who chose activity B. And because we're only looking at one column, this proportion who chose C is greater than those who chose B for that. And consequently, we can say that because we're within one column. As we're looking at one column only, we can talk about the number. We cannot talk about numbers when we're going across multiple columns. Number 33. At a large airport, data were recorded for 1 month on how many baggage items were unloaded from each flight upon arrival, as well as the time required to deliver all the baggage items on the flight to the baggage claim area. A scatter plot of 2 variables indicated a strong positive linear association between the variables. All right. Which of the following is a correct interpretation of a strong in the description of the association? Well, first off, I'm going to draw a couple little graphs here. If I have a graph like this, that is a pretty strong and upward sloping positive. Whereas I could have a graph like this, and it's like, yeah, that's still sloping up, but it's weak. All right. Yes, it's definitely, we definitely have an upward slope, but it's definitely weaker than this one. So consequently, I feel pretty good about making a prediction on this because I have small residuals, all right, and I'm going to have a high correlation. So this will have a strong positive correlation. This will have a weak correlation. This has large residuals. This has small residuals. All right, so let's continue on with this problem and look at our answer choices. Okay, a least square model predicts that more baggage items are unloaded from a flight the greater the time to deliver the items. That's true. The more unloaded, the more time. That's true, but that doesn't indicate the word strong, right? So that didn't help us with the word strong. That is a true statement, though. The actual time required to deliver all items to the baggage claim area based on the number of items unloaded will be very close to the time predicted. And here's my prediction line, and I can look and go, gosh, it really is close. That's my best answer. It's going to be very close to what's predicted because it's a strong relationship. Or over here, yeah, it's positive, but it's a weak relationship. The prediction is not nearly as good. We're not going to be nearly as close. Number 34. A group of men and women were surveyed to investigate the association, there's a key word, between gender and the number of friends the person has on social media website. Results are shown in the table below. All right. Well, immediately I like, okay, we have two genders, but I have multiple categories. As soon as I see multiple categories, I'm thinking chi-squared. They use the word association. I'm thinking chi-squared independence unless something pops up. Which of the following procedures is the most appropriate for investigating whether an association, whether or not they're independent or dependent, exists between gender and the number of friends? And I see real quickly that I have chi-squared. All right. But because it's association, this makes it a test of independence. This is one of the more challenging problems. Carly commutes to work and her commute time is dependent on weather. When the weather is good, the distribution of her commute time is approximately normal with a mean of 20 minutes and a standard deviation of 2 minutes. So if it's good, I'm just going to put a G for good. That does not look like a G. This is good. We have a mean of 20 and a standard deviation of 2 minutes. When the weather is not good, so I'm going to call it bad. I know they're saying not good. We have a mean of 30 with a standard deviation of 4. So our mean is 30 and our standard deviation is 4. Suppose the probability the weather will be good tomorrow is 0.9. So we have a probability of good equaling 0.9. That means the probability of bad is going to be 1 minus that, which is going to be 0.1. And all I did is 1 minus 0.9 gave me 0.1. You need to sum up to that. Suppose the probability, which of the following is closest to the probability Carly's commute tomorrow will be greater than 25 minutes? So I want to know the probability that it's greater than 25 minutes. But it could be greater than 25 minutes over here as well. So I'm going to need to do the normal distribution twice. All right. So I want the probability that X is greater than 25. And over here, I'm going to want the probability that X is greater than 25. And I can do a normal CDF, and I'm going to do it for both of them. Stat test, excuse me, second vars, normal CDF. My lower bound is 25. My upper bound, she may never get there, positive infinity. My mean was 20, and my standard deviation is 2. And I get a value of 0.0062. So that's the probability that it takes more than 25 minutes if it's a good day and there's a 90% chance that it's a good day. But there's possibility that it's a bad day. So what's the probability that, how long does it take us to go that far on a bad day? Well, second VARS, normal, CDF, 25 minutes is still my lower. That's what I have shaded. My upper bound is infinity. My mean is now 30, and my standard deviation is 4. And I get 0.8943. 0.8943, but there's a 10% chance that that happens tomorrow. So let's do that work real quickly. 0.9 times 0.0062 plus 0.1 times 0.8943. And I get 0.09501. So my closest answer is letter C. Now what's important here is basically I did the probability that Z was greater than 25 minus 20 over 2, and I got 0.0062. That was my answer. But there's only a 90% chance that that would happen. Over here, I did the probability that Z was greater than 25 minus 30 over 4, and I got a probability of 0.8943. There's only a 10% chance I'm going to get stuck with that. Okay, and it's either going to be good weather or it's going to be bad weather, so I can add them directly. Okay, so that's how that problem is done. That was definitely a more challenging issue. Number 36. The number of siblings was recorded for each student of a group of 80 students. Some summary statistics and histogram displaying the results are shown below. So we have a mean of 3.5, a standard deviation of this, Q1 of 2, Q3 of 5. An outlier is often defined as a number that is more than 1.5 interquartile ranges below the first quartile or above the third. Using the definition of an outlier and the given formula, which of the following can be concluded? The first thing it starts with is the median is greater than or the median is less than. Well, I look at this and I see skewed right. And if I see skewed right, that means my mean is greater than my median. All right, so my mean is greater than my median, or my median is less than my mean. So the median is greater, that gets rid of these because we know the median is less than. So we know we're going to be looking at a D or E. And then it says I need to calculate outliers. All right, so to be an outlier, X has to be less than Q1 minus 1.5 IQR. So let's calculate our IQR. IQR equals Q3 minus Q1, which in this case is 5 minus 2. IQR equals 3. So Q1 is 2. 2 minus 1.5 times 3. I know I'm going to get a negative number, but I'm still going to calculate it. 2 minus 1.5 times 3 is negative 2.5. X is less than negative 2.5. We don't have anything below 0, so we can't have any outliers on the lower side. On the upper side, our outlier is X is greater than Q3 plus 1.5 IQR. Well, Q3, they tell us, is 5. So 5 plus 1.5 times, we already calculated an IQR of 3. So 5 plus 1.5 times 3 is 9.5. So X has got to be greater than 9.5. All right. Well, 8.5, 9.5, so it has to be greater than this line. When I look here, I say, oh, I have two little bars, they come up to 1, so I have 2 outliers. My answer choice, 36, is E. All right, 37. In the states of Florida and Colorado, veterinarians investigating obesity in dogs obtained random samples of pet medical records and recorded the weights of dogs in the samples. A test was conducted of the P1 equals P2 and P1 does not equal P2. This is going to be important. Where P1 represents the proportion of all overweight dogs in Florida and P2 represents the overweight dogs in Colorado. The resulting test statistic was for 2 sample Z tests, which was nice of them to tell us, but they didn't have to. They told us it's proportion, and if it's proportion, we know it's a Z. All right, anytime it's proportion of Z, was 1.85. So they got a Z value of 1.85. At the significance level of 0.05, which of the following is a correct conclusion? Well, they didn't give me a p-value, so I need to calculate a p-value. Well, they did give me the test statistic. Because they gave me the test statistic, I can get a p-value. So here's my graph of my z-scores. Please remember, z-scores are centered on 0, so we have a 1.85 as my z-score. And we're always looking for more extreme, which is in this direction. So second vars, normal, CDF, lower bound, 1.85, upper bound, infinity, z-scores are 0 and 1, 0 and 1, and I get a p-value of 0.0321. But hold on, we only went one direction. We only did a greater than, and this is a not equal to. So I also need for negative 1.85, and I don't even have to calculate it because it's symmetric, which is 0.0321. And so once you've calculated a one tail, you have to double it, so times 2. So my p-value for this test is 0.0643. My p-value is 0.0643, which they gave us an alpha of 0.05. So if we have a p-value and we have an alpha, this is 0.05, this is 0.06, this is greater than, we fail to reject. So we fail to reject the null. That means there's not sufficient evidence. So let's see what we have. There is not sufficient statistical evidence to conclude that the proportion of all overweight dogs in Florida is different from the proportion of all overweight dogs in Colorado because the p-value is greater than 0.05. I like that answer. They are very tricky and they put the Z statistic here, but that's not right. We're supposed to compare p-values to alpha. Okay? All right, so that's 37 is A. Number 38. A newspaper editor wants to investigate whether residents of the city support a proposal to build a new high school football stadium. The editor hires a polling firm to conduct a survey and requests that a sample of 500 residents be used using a stratified sampling based on voting district within the group. So as soon as they tell you it's stratified, you know you're breaking it into groups. Here we're breaking it to groups based on districts. So we're going to break it into voting groups, and then within each voting group, we're going to conduct a random sample. Remember, you break it into strata or you're into the groups and then do a random sample. That's a stratified. So which of the following will achieve the sampling design? Send a survey to all residents and use the first 500 to return. That's biased, etc. Has all sorts of issues. Select a random sample from each voting district based on the proportion. That sounds really good. We're going to each voting district and we're taking a random sample from each voting district. That's possible. Select one voting district at random and then select no. Selecting one voting district, that's not it. We're supposed to get all of them. Alphabetize, all the rest of these don't apply. The only good answer is B. 38 happens to be B. Number 39. A simulation was conducted using 10 fair-sided, six-sided die, where the faces were numbered 1 through 6. All 10 were rolled, and the average of the 10 numbers appeared facing up was recorded. The process was repeated 20 times. Which of the following best describes the distribution being simulated? We don't care about how many times you report the process. That doesn't apply. What applies is the 10 dice. So anything with the 20 doesn't matter. All right. So how do I do this problem? Well, they didn't give me the mean. They didn't give me all that information. So I'm going to go to my calculator. I'm going to go to stat edit. And I'm going to enter 1, 2, 3, 4, 5, 6 into the calculator. I'm going to go stat calc, one variable statistics. My list is an L1. And I end up getting a mean of 3.5. All right, so we know the mean is 3.5. So that gets rid of this one. All right. So we have 3. So now we're down to 2 answer choices. So standard if we're doing the sampling distribution of X bar is going to be the standard deviation divided by the square root of n, which in this case is 10. And we have a standard deviation of 1.707. And you're like, why did I choose the 1.707? The reason I chose that is because if I have a 6-sided die, it doesn't matter how many times I do it, all 6-sided die have that standard deviation. All 6-sided die are going to have the 1.707. So it's not a sample. That is what the population has. So 1.707 divided by the square root of 10. And I end up getting about 0.54. My best answer choice is A. Okay. All right, number 40. The SC Electric Company has bid on 2 electrical wiring jobs. The owner of the company believes that the probability of being awarded the first job is 0.75. The probability of being awarded the second job is 0.5, and the probability of being awarded A and B is 0.375. I'm going to go ahead and draw a Venn diagram, even though I normally don't use these. I think it'll be informative here. And I'm going to call this A, this B, this is 0.375, because that's my overlap. And 0.75 minus 0.375 is 0.375. And 0.5 minus 0.375 is 0.125. And of course, I have this area out here, 0.375 plus 0.375 plus 0.125 minus 1 tells me the area out here is 0.125. So the probability they don't get anything is 0.125. Okay. If the owner's beliefs are correct, which of the following statements must be true concerning event A and B? Event A and B are mutually exclusive. They cannot be mutually exclusive. Mutually exclusive means there's no overlap. We know we have an overlap of 0.375. Events A and B are mutually exclusive. No. Events A and B are not mutually exclusive and are independent. Well, if they're independent, the probability of A times the probability of B needs to equal the probability of A and B. If they're independent, that's true. So let's check it out. 0.75 times 0.5. Let's multiply that out. 0.75 times 0.5. Oops. 0.75 times 0.5 equals 0.375. And up here, they told us that intersection is 0.375 because these two multiply to equal the intersection, they are independent. All right? They are independent. Remember, if you have any overlap, they cannot be independent. And in this case, we have an overlap of 0.375, and A times B equals the overlap. And if A times B equals the overlap, then they are independent. All right, that concludes this one.